Hello, and welcome to the lesson on section 12.5, Alternating Series. In this lesson, you'll learn what an alternating series is and how to determine whether an alternating series is convergent or divergent. We'll also look at a method for estimating the maximum error in calculating the sum of a convergent alternating series. In an alternating series, terms are alternatingly positive and negative. The formula of an alternating series typically contains a -1 raised to a variable power, or sometimes you may see something like the cosine of pi times n, or the sine of pi over 2 times n, which also goes back and forth between +1 and -1. In example 1, I'll use a calculator to examine some partial sums of the following alternating series. For the first series, press alpha window on your calculator to pull up this menu and select number 2, summation. You can see that it doesn't take many terms to see that the series appears to converge to 2/3. In fact, we didn't really need a calculator for this one. This is a geometric series with first term 1 and common ratio -1/2. If I use the formula for the sum of an infinite geometric series, I'd get 1 over 1 minus -1/2, which is 1 over 3/2, or 2/3. For the second series in this example, the partial sums I found on my calculator appear to diverge. Let's take a look at the first few partial sums without using a calculator. The first partial sum is just the first term, 1. Subtract 2 from that to find the second partial sum. Add 3 to get the third partial sum. Subtract 4. Add 5. Subtract 6. Add 7, and so on. You can see that the partial sums will continue to follow this pattern and thus will diverge. So why did one alternating series converge and the other diverge? By the alternating series test, if the absolute value of the n plus first term is less than or equal to the nth term, in other words, if the absolute values of the terms decrease, and the limit of the absolute values of the terms is 0, then the alternating series converges. In the second series of example 1, the absolute values of the terms increased. This caused the partial sums to grow further apart instead of drawing closer together as we continue to add terms. In example 2, I'll use the alternating series test to determine whether the alternating harmonic series converges. Just like it sounds, the alternating harmonic series looks just like the harmonic series 1 over n, except that it alternates. First, I need to show that the absolute values of the terms decrease. 1 over n plus 1 is the n plus first term, and 1 over n is the nth term. Since the denominator of 1 over n plus 1 is larger, it's the smaller of the two fractions. As with the comparison test, you can assume this comparison is obvious as long as the numerators or denominators in the two fractions are equal. As another way of showing that the n plus first term is always less than the nth term, I could have calculated the derivative of the absolute value of the nth term formula and shown that the derivative is negative for all n greater than or equal to 1. Next, I need to show that the limit of the nth term goes to 0, which it does. Therefore, the alternating harmonic series converges by the alternating series test. Here's a proof of the alternating series test, which is also called Leibniz's theorem. Suppose we have an alternating series with formula -1 to the n plus 1 times a sub n. This series is written so that a sub n already represents the absolute values of the terms. The nth term is greater than or equal to the n plus first term for all values of n, and the limit of a sub n as n approaches infinity is 0. Let's make a sequence out of the partial sums for even n values. So for now, suppose n is an even number 2 times k. Then the sum of the first 2k terms is a1 minus a2 plus a3 minus a4, and so on up to a 2k minus 1 minus a sub 2k. This partial sum is greater than or equal to 0 because a1 is greater than a2, a3 is greater than a4, and so on. Each of the groups is positive. Thus, s sub 2k is bounded below by 0. The next term in the sequence of partial sums is s sub 2k plus 2, where 2k plus 2 is the next even number after 2k. This equals the previous partial sum plus the next two terms after a sub 2k. Because the group in the parentheses again has a positive sum, s sub 2k plus 2 is greater than or equal to s sub 2k. Repeating this pattern, we could show that s sub 2k plus 4 is greater than or equal to s sub 2k plus 2, and so on. Thus, the sequence of partial sums is strictly increasing. If I take the terms of s sub 2k and group them differently, I can see that the sum results from subtracting positive numbers from a sub 1. Thus, s sub 2k must be less than or equal to a sub 1. And therefore, s sub 2k is bounded above by a sub 1. I showed on the previous slide that s sub 2k is bounded below by 0 and that it's strictly increasing. Therefore, by the monotonic sequence theorem, the sequence of partial sums converges to some real number L. If you've forgotten the monotonic sequence theorem, it might help you to remember that we used this theorem to derive and show the convergence of a sequence that approaches the Champernowne constant, which contains the text of every book ever written. Suppose now instead that n is an odd subscript. Then it can be expressed as 2k plus 1. Then the partial sum s sub 2k plus 1 is equal to s sub 2k plus the 2k plus first term. The limit of this partial sum as k approaches infinity is equal to the limit of s sub 2k plus the limit of a sub 2k plus 1. We've already shown that s sub 2k approaches some real number L, and it's given that the limit of a sub n as n approaches infinity is 0. Thus, the limit of the partial sums with odd-numbered subscripts is also L. Since both the even and odd-numbered partial sums approach some finite value L, the series converges. The last topic of this lesson is estimating the sum of an alternating series. Suppose we use the nth partial sum to estimate the actual value of the sum of a convergent alternating series. Then the error in estimating the sum in this way will always be less than or equal to the value of the n plus first term. Very informally, if you think about how the partial sums of a convergent alternating series work, every time we add a positive term, the partial sum overestimates the actual sum. When we subtract the next term, the partial sum underestimates the actual sum, but by a little less. We'll talk more in class tomorrow about why this error calculation makes sense. Let's look at how this error calculation would work with a geometric series that alternates. I'm choosing to work with a geometric series because we know how to calculate its actual sum. In this course, we'll usually only be concerned with whether a series converges or not, instead of what value it converges to. For the most part, you'll only be asked to calculate the sum for a geometric series. Earlier in this lesson, we calculated the sum of this series to be 2/3. Let's say I use the partial sum s sub 4 to estimate the sum. Then the error in using this partial sum to estimate the actual sum should be at most the value of a sub 5, which is 0.0625. The actual error is 2/3 minus 0.625, or 0.0416 repeating, which is less than the fifth term. This concludes the lesson on section 12.5, alternating series.